So, welcome to this, the first of a set of videos where we will discuss the topic of tuning the data warehouse. In this video we will talk about physical design issues such as table design, table spaces, compression, materialized views, vertical and horizontal partitioning, among others. So, what is physical design? Well, usually you make a distinction in database methodology between logical design and physical design. So when we talk about logical design, we usually talk about the abstract representation of entities, right? Of entities and those entities' attributes and the relationship between those entities. And then you could say that an entity maps to a physical table in a database, and an attribute maps to a physical column in a database. So physical design deals with the actual actual entities, or well, at least the digital the actual digital entities in a database, in an actual database that is actually created in a database management systems, in a DBMS. So physical design, we could say, is the effective way of storing and retrieving the data. And usually when we talk about physical design, if you, for instance, have a database methodology book, in many database methodology books you will see that you will have like a chapter dealing with physical design, and there you will find discussions on materialized views, aggregates, indexing techniques, partitioning, and so forth. While in other books you will find some of those topics under the logical design chapter. So we don't have a final say in the distinction between logical design and physical design. And sometimes, most often, you don't need to have that exact definite distinction, and sometimes it might be useful to have such a distinction. So here I will present an example of such a distinction that sometimes might be useful when we talk about logical design and physical design. However, during this video we will not really care that much if this should be defined as logical design or physical design. We will say that we will have a more relaxed approach and say that things that will be implemented in the database, that is what we call physical design. However, Golfarelli and Rizzi, who has written a really interesting book on data warehouse design called Data Warehouse Design: Modern Principles and Methodologies. And in this book they states the term physical design should include only those operations linked to specific features of the database management systems, such as choices of indexes and adjustments of allocation strategies. So here we have a really distinct separation between the two topics, the two things. So we will say that physical design needs to have specific features in the database management system. So physical design deals with database management system specific issues, while logical design is operations that you can design actually before you know which database management system you will use. So this is an extract from their book, and a figure from their book, Golfarelli and Rizzi's book, where we can see here this very, very distinct. You can't have a more distinct line okay, you could have it filled, but it's a very distinct line. And then they say fact schemata translation. So this operation, this deals with actually translating the logical design into the physical design. That translation is in the logical design. And then we look at view materialization. As you are all aware of, we have in SQL, we have views where you, for instance, can join. You can create a statement, create view on something, and then blah blah, and then you will then you can call this view in the from statement in your SQL statement. And so you can say in the from clause you can say the name of the view, and then each time you ask for that view, the create view statement will be run. In a materialized view, then you pre-calculate this, so you store the result from the create view statement as a physical table, which of course when you access that view, it will be faster. So view materialization might be a physical design, no, sorry, a logical design. You see, it's not easy. You can see that as a logical design operation to improve performance. And then we also have vertical and horizontal fragmentation, which deals of dividing, fragmentizing tables, so you have a subset that is more manageable, the subset of a table that is more manageable. So you have smaller sets of data, basically, which sometimes might be more efficient. But all this you can design without even knowing what database management system you will use. If you will use DB2 or Microsoft SQL Server, or if you will use MariaDB or MySQL or any other Oracle's databases or any other. And then you have this distinction, and then you say choice of indexes. Well, it's very different. In some database management systems, you can use some indexes techniques, and in some you can use others. So this is really database management system specific. And allocation of data to physical media, well, that is also database management system specific. So I would say that the first three, fact schemata translation, view materialization, and vertical horizontal fragmentation, that are general functions. And choice of indexes and allocation of data to physical media is DBMS specific functions. And then in this figure from Golfarelli and Rizzi, we also have an operation called performance adjustment. And performance adjustment, it has to do with SQL optimizers. In all database management systems, you actually have an built-in optimizer that, without you knowing it seamlessly, changes your SQL queries into more optimized versions. So it evaluates your SQL query and then rewrite the query execution plan that is used. What this means is, for instance, if you're kind of a poor SQL author, you might write a SQL query that where you first, in the beginning, you compare two large sets of data, and then at the end of the query you say, well, only some of the rows in all this data are interested in our comparison. So that means that you will do predicate searches on a lot of data, which is very exhausting performance-wise, and then you will make a selection later. So this is not very optimized. So then the SQL optimizer will will say that it's better to first filter out the important rows and then compare two smaller sets of data. So this will be more efficient because we don't have to touch as many rows. We don't have to go through a lot and do comparisons on a large amount of data. We filter first and then we just check the few rows that are left. And you won't know. You will have your SQL statement and you will be very proud of it and think, oh wow, I'm such a good SQL author. But it's actually the automated optimizer that has rewritten your query and made it more efficient and let it have a more efficient query execution plan. So that's life. But then this is kind of interesting when you look at the distinction between logical and physical functions, because performance adjustment, this SQL query optimizer, that is really DBMS specific. So as you see here, it's really on the border. It's right on the border, because it will also utilize some of the logical design operations. So it will look at what materialized views do we have, and then perhaps if we write a poor query, then the SQL optimizer would say, hey, look, we have a materialized view here, and we will use that instead. And and it will also look at the vertical horizontal fragmentation, and then look at, okay, we don't have to look at the whole table, let's just look at this fragment of the table, this subset of the data that are interesting, that will be needed for this query. So performance adjustment is on the border of logical and physical design. So even in this distinction, you can't distinct always. Right. So moving on. This is a DBMS specific optimizer, and but on the border. So according to Kimball, in the third edition of his Data Warehouse Toolkit book, he lines out 4 different parts in the physical design. So he says, developing naming and database standards, develop physical database model, develop initial index plan, and design aggregations. So of these 4, developing naming and database standards, we will not discuss in this course or in this video, but just an example for the students from the IS5 course, we have made some of those, we have created some of those standards. We have said that in this course we use camel case. So camel case is a way of writing table names and attribute names, where you have a lowercase first letter in attribute names, and so think of Java. They use this camel case, and the word camel case is actually written as a class name or a table name in camel case. And then we have chosen TSQL, transaction SQL or transaction SQL, depending on how you want to pronounce it. And TSQL is a Microsoft specific branch of SQL. The TSQL we will use in this course is adapted for Microsoft SQL Server 2012. So these are some of the physical design standards or decisions that we have chosen for this course. And then in your database project or data warehouse project, you will choose your own thing. So the important thing here is not what is what your teacher has taught you, but that you all use it within your team when you work on this, right? So this camel case, TSQL, Microsoft SQL Server 2012 are just something that we choose. It should not be considered as better or worse than or for instance an Oracle version. At least we don't address those issues here. And then the second step, develop physical database model. There we will that step concerns logical design implemented in a DBMS, and here that star join schema is translated into DBMS, and what optimization techniques that could be used when we translate and create the physical database. So this is what this video will deal with. Then in the next videos we will talk about developing an initial index plan. That will be the next video. And the third video in the physical design series for this course will be designing aggregations. And what we can see here, that developing physical database model, here we address performance optimization. That is a really important topic, and that's what this video will talk about a bit more, or introduce you to some topics at least. And then developing initial index plan. This of course also addresses performance optimizations, and so does design aggregations. So let's move on. Develop the physical database. So here we have some optimization issues. We have OLAP databases and OLTP databases. OLAP means online analytic processing, and OLTP means online transaction processes. So traditional databases that is used in the operational business is called OLTP because they deal with transactions. That's what the T is for. They deal with registering sales or capturing changes in the staff or things like that. While OLAP is databases that are designed for analyzing data. So when we compare those two different approaches on databases, we can see that, for instance, joining table, if we have a lot of joining table or a few of them, then we will see that in OLTP we'll have many table joins, because we will have denormalized tables and a large amount of tables. And in OLAP, well, there we will deal with normalized databases with very few tables. And when we look at duplicated data, again, normalized table brings together a lot of data, and instead of having 3 small tables, we join them into a big table, and OLTP does the opposite. So duplicate data, it will be an issue when we have normalized data. So in OLAP, duplicate data is common. In OLTP, it's very rare. And when we talk about derived data and aggregates, well, in OLTP, we don't store derived data, and we don't store aggregates. We calculate them if we need them, because we don't want to have duplicate data and to we look at inserting issues, rather than analyzing issues. So we will see that in OLTP, derived data and aggregates are very rare, while in OLAP they are very common, because if we pre-calculate things, then it's much faster just to fetch the data if we did the calculation earlier. And in OLAP we often have to do calculations. And then the fourth issue in this slide will be the indexing technique. And indexes, as you are all aware of, it's like when you have a book and you look for a certain topic in that book, rather than reading the whole book until you find that topic, you can actually just go to the back of the book and then find the index, and then you will have a page indicator. When you find your topic, you will just read through the index, and then you will find your topic, then you will have a page indicator. In a database, it's very similar. Instead of going through the whole table, you can go to the index, look for your topic, and instead of a page indicator, you will have a row indicator, a RID, row identifier. So you will have a RID, and then you will just go to that row ID, and then you will get your data. So in OLTP, there's a few, and in OLAP, we have many indexes. Because when you create an index in OLTP, if you create a new instance of the data, and if you add a new row, if you have many indexes, well, you need to update the table, of course, but then you also need to update all the indexes that you have created, and that's not very efficient when you want to be able to very quickly add new transactions, new sales, for instance. While in OLAP, well, you don't have to consider updating or inserting new data. You just read the data, and then as many indexes based on different attributes, the more the merrier, right? So the effect on performance, of course, is also interesting. In ETL process, we talk about how we extract, transform, and load data into the data warehouse. While in OLAP, online analytical processing, we rather talk about how we read or how we retrieve data, how we access data from the data warehouse. So if we look at the same four topics, then we can see, well, if we look at joins, we will see that a lot of joins is very positive for the ETL process because we have to deal with less data. A lot of joins means that we will have no duplicate data, and it will be very correct data because we will have referential integrity that will help us have good data. However, when we retrieve data from the database, joins is negative because it creates more complex queries. And if we have more complex queries, then for instance, the SQL optimizers will have a much harder time, and even it might be impossible for SQL optimizers to create a more optimized execution plan because it's too complex. And of course, it also takes some time to join tables. It's not that big of an issue. However, in data warehousing, sometimes you hear about, you should avoid combining tables and avoid joins because it takes so much time. No, it's not that big of a deal. The reason is rather that it adds complexity. And then, of course, we have the duplicated data, and then we will see, well, duplicated data means more data, and of course, when we will extract and load, and when we load data into the data warehouse, if we have a lot of duplicate data, that will make it more complex in the ETL process, so it will affect the ETL process negatively. While OLAP, if we can access data in several places, it will be faster to access it. If we have one table where we have all the data we need, it will be faster to access it. And in derived data and aggregates, if we pre-compute data, for instance, pre-compute sums or aggregate data, that we need to do in the ETL process, so the ETL process performance will suffer from this, while the OLAP process will benefit from it. And the fourth topic, indexes. Of course, if you have a lot of indexes, the ETL process have to deal with more, while the OLAP process, it will be more positive. And of course, in this case, OLAP is our favorite child. We will need to address the issues of OLAP performance first. And then later in this course we will talk about ETL performance, but we will always, when we design a data warehouse, we will always look at the OLAP process as the top the top demander, the top customer, our favorite child, which we will give everything. And ETL is the black sheep in the family, which we will need to deal with later during the next lecture. So we make sure that OLAP is as efficient as possible, and then we fine-tune the ETL process, and then we will have things we can do. However, we will not address it in this video. So here are some common topics, some common issues in physical design. So for instance, when we talk about table design, we can talk about compression. Compression, it's really great. You can reduce a table to its half size, and if you have like a table with 100 or 200 or even million of rows, then a half size is really beneficial. It will be so much faster to go through all that data, nearly the double time, right? However, it will lead us to have slower DML, because the insert, update and merge statements will of course need to uncompress and then insert the data and then compress again. So it will really slow down insert, update and merge. And this, of course, it's a problem in transaction operational databases. It's not a problem in analytical structured databases, as we really much care for read performance than insert performance. So faster full table scans, that means that compression can be used with great benefits in data warehousing databases. Table spaces. Well, table spaces is a logical subdivision of the disk space used by a database. So table spaces separates physical data on different table spaces, and it's dependent on an operation system. It must store this uniform data sets. You can't have different data types, for instance, and it helps us manage the size of data chunks, and it is invisible to users. So you might store one table on different table spaces, and then you can retrieve them more efficiently. You can also, apart from dealing with table space, you can also deal with data files, sometimes called segments, which is a file storing part of the information on a table space. A data file belongs to a single table space, and a number of data files might be associated with one table space. So it's a sub-part of a table space. And then finally we will have the disk blocks, where we have a number of bytes where we can store the data. And a disk block is the information unit read or written by the DBMS. And then if we have large 64-byte table blocks or so forth, we can have more efficient data reads, for instance. All this compression and table spaces, it's invisible to end users. Then if we take a step up, we will have RAID solutions, which is for instance RAID 0 is about disk mirroring. That means that whenever you store some data, you will store a copy of it on a mirror disk. This is usually, it was created to solve that if one disk goes down, well then we will always have a copy of that disk. So every time you make a change on the data, you will have two disks with the same data, and if one goes down, you will always have the other. So disk mirroring is very good for for security, of course. But if we look at in a data warehouse, well, disk mirroring means that we will have it will updates and changes, updates, inserts, and changes on data will take longer because you have to write the same data onto places. It will take up more resources, and it will probably take more time. However, when you read, then you can read some of the data with using one CPU on one disk, and using perhaps another CPU on the other disk, and collecting the rest of the data. So then you can actually access the same table from two ends, so to speak. So in that way, for instance, disk mirroring rate 0 might be beneficial. There's other RAID techniques. You have 1, 2, 3, 1, 3, and 5. I guess is most used, but they usually have more to do with backup and security and so forth. But they and that, of course, is something that you need to look into, even if you build a data warehouse. But perhaps it's not that interesting from a performance. Well, yeah, I guess it has some implications there as well. I don't know that much about it, so I should not say too much, I guess. We have materialized views. We have SQL views stored physically. So I talked a bit earlier about that when we create a view, instead of running the create view statement each time we access that view, we can actually store the view physically on the disk as a table of its own. And this is done when we have pre-calculated aggregate tables. We will talk about aggregates in another video. And when we have pre-joining tables. So instead of running a join on 2 tables or 4 tables or a star join schema, we can actually have a pre-join table stored physically. This is also invisible to the user. Much of the physical design issues are not shown to the users. It's physical decisions and physical solutions rather than logical, visible for the end user. SQL queries are redirected to the materialized view. For instance, if we write one of our poor SQL queries, creating a view and then accessing that view, the SQL optimizer will say, hey, that view is, we already have that view stored, physically stored, so I will go to and look in that physically stored view rather than using your poor SQL statement. So that's how the optimizer, again, somewhat annoyed, but however still helps us with the performance in our database, in our accessing our database. So do not use materialized views when the view is nearly the same size as a base table, because then you won't benefit from it. It will just be that you store the same data twice, but it's almost the same data in both places, and you can't benefit from that. So create views if you need them, store materialized views if there are a great difference between the materialized view and the original table. But if they are almost the same, perhaps then just one join or something like that is more beneficial. If performance is eaten up by refresh, perhaps you should reconsider using the view. And if you suffer from aggregate sparsity failure. What is aggregate sparsity failure, you might ask? Well, I will talk about that in a later video, the video on tuning data warehouses by using aggregates. So the third video in the series will deal with that. Okay, so let's end this video by saying a few words on partitioning. So usually you talk about horizontal and vertical partitioning. So if you have a table, think of that you have the rows vertically, I guess, and the attribute horizontally. But when you split the rows on the vertical end, you will split them horizontally, right? So if you partition, if you fragment a table that you have one chunk of rows in one table and one chunk of rows in another table, then you have partitioned them horizontally because the split is horizontal. Well, then you can also, if you have a database table and you want to split it, you can also split it that you say that instead of having all attributes but some of the rows, that was the horizontal, you can split vertically between the attributes. So you have one set of attributes in one table and one set of attributes in another table. And when you do this physically, in two different tables, then you talk about physical partitioning, horizontal and vertical partitioning. The vertical partitioning, think of mini dimensions and outriggers in the data warehouse terminology. However, in data warehouse terminology, we can actually logically say that, okay, now we define, we partition these tables vertically, logically. But here we are talking that we also do it physically. And sometimes a mini dimension is, very often of course, a mini dimension is physically a vertical partitioning. But it doesn't have to be, as we will see in the examples. So partitioning speeds up table scans, and yes, in mini dimensions. So look at horizontal partitioning. So horizontal partitioning has to do when we do the split horizontally. So that means that we split between the rows. So in the logical design, we will have a sales fact table, time, product, key, store key, dollars sold, units sold. And the physical storage says that, okay, 4 rows, the first 4 rows we will have with time key 1, 2, 3, and 4, and key store 1, 1, 1, 1, and they are together primary key, of course. So then we will see that these are 4 rows with values on sold units and units sold. And then when we look at the lower table here, we will see that these are 4 different rows. It's the same time keys, 1, 2, 3, 4, so it's the same dates. But here we talk about a different store. So these are different rows in the fact table, and we store some of the rows, these first 4 rows, and of course more, we store in one table, and the rest of the rows we store in the second table, but it's the same attributes. However, the user might be very confused over this, so we won't show this to the user. So if we look at the physical storage, we have sales store 1 with the first row from key store 1, and we have the sales store 2 with key store 2. What we do then is that we have a logical visualization. That is the logical design, basically, where we have our 2 logical model tables, sales store 1 with the rows from sales store 1, and the logical design of sales stores 2 with the physical rows from sales stores 2. And then we use union to union these 2 rows. So we union sales store 1 with sales store 2, so we'll have all the rows from the first set, and then we union them with all the rows from the second step, and then we will have logically just one table visible for the users. So users won't know that we actually have 2 tables, right? 2 physical tables. For the user, it will still just look that we have one, the sales view. So this means that the user is not aware of the breakdown of the data. So that was horizontal partitioning when we split horizontally. When we split vertically, when we split between the different attributes, then we talk about dimensions or tables with a high degree, so high degree relations with a lot of attributes, and then they are split into smaller relations, each with an exclusive subset for non-key columns. So here we won't have the same non-key columns. The attributes will be different in the two attributes. And performance issue 1 deals with this vertical partitioning. We talk about here rapidly changing values. So we have, throughout this course, we have used the example of demographic data because it's a very good example, because demographics of people change very rapidly. People change their income, they might move, they might get more kids, they might separate, they get married, they do all these life things that I'm sure you all have heard about when you look away from your books 5 minutes or so. And these demographics change very rapidly, and then it could be good to separate the rapidly changing data from the data that doesn't changes, and then we would perform a vertical partitioning. And we can do this physically, and we can do it logically, and we can do it both logically and physically. Think of mini dimensions, for instance. So here we have order lines that never changes, order lines that seldom changes, and order lines that frequent changes, and then we have different tables for them. Performance issue 2 on large free-form text columns for more efficient free text searches. So if we have, for instance, some application that is very heavy on performance, for instance, if we have a table with one thesis per cell or one book per cell, and then we have some data mining technology that goes through all this free text, this free-form text, and searching for patterns or something, then we might want to lift those attributes out to a different table, so when our ordinary users, or when we do our ordinary searches, we don't have to use the same tables as those very heavy, performance-wise heavy applications use. So then we can separate those heavy attributes from the others. We will talk more about free text searches during lecture 9 on data mining, where Hercules Dalani, a professor at DSV here at Stockholm University, will talk a bit more about how you can use data mining, for instance, in free text searches. Yes, and then we'll finish off with vertical partitioning, performance issues 3, and that it's kind of similar to performance issue 2. Here we will have some attributes that takes really a lot of space, for instance blobs, big pictures, big models, perhaps applications of their own, something very big and complex in one attribute. So the data type would be blob, for instance. There are several big data types. So smaller rows take less space, and smaller rows means that database management systems can buffer more rows. And buffer, that means buffer in the working memory, in the electronic memory, instead of having all the information on disk, because retrieving data from disk takes much more time than retrieving it from electronic buffers from the primary memory in a computer. So we want to be able to use buffers, and we can't have as many rows in our buffer memories if the attributes are too big, because then we can't have that many rows. So then you could use vertical partitioning and lift out those very large objects to another table, and then have the smaller attributes in another table. So that means that when we do our searches on the table with the smaller attributes, then those searches will be very much more efficient, because we don't have to scan through all these big blobs, which take times, and we don't have to rebuffer all the time, because we can have larger chunks of data in the buffer at one time. So separate very large attributes from smaller attributes into different tables, and then of course searches even in the blob table, so to speak, will be faster, because we don't have to deal with the huge amount of attributes, perhaps. The beautiful pictures from this book is from a songbook from early 15th century. It's called Codex Manesse. Codex Manesse is you can use it freely, so so I have used it here, and very happily used it here. And you can access it from the University of Heidelberg at dg.ub.heidelberg.de. So look at they have many fantastic books which you can access from the web, and well, that's all I have to say about that. Thank you for your attention.